Let's learn how numbers stored in JavaScript using IEEE 754 standard. In JavaScript, all numbers are stored in a 60-bit floating point format, also known as double precision floating point numbers. IEEE 754 is a technical standard for floating point computation. For those who are curious, IEEE stands for Institute of Electrical and Electronics Engineers. According to this IEEE 754 double precision format, every number in JavaScript is stored as 64 bits in memory. This 64 bits is composed of three components: sign, exponent, and mantissa or fraction. If we are given a random decimal number to convert to binary, we have to write our decimal in a format similar to the equation shown below. Sign bit shows if the number is positive or negative. If positive, sign bit will be 0. If negative, sign bit will be 1. Fraction or mantissa represents the precision bits of the number. Exponent is like a scientific notation. For example, we can write 100 as 1 times 10 power 2. 2 is exponent here, but here our exponent is biased. What does that mean? Biasing is done to represent both very tiny and large values. For example, 0.001 can be written as 1 times 10 power minus 3. Here minus 3 is the exponent. So not to have a negative number, we add bias. In double precision format, the bias is 1023. Why specifically I said 1023? Because for exponent we have 11 bits allocated. Then for bias we are allowed to allocate only 10 bits. And remember from the previous decimal to binary video, if you have only 10 bits in binary, our number decimal should be lower than or equal to 2 power 10 minus 1, and it is 1023. Maybe it does not make sense because I'm just talking. The best way to learn is by practice. I will convert one integer and one floating point number to binary using IEEE 754 double precision format, so you can learn. Let's convert 9 from decimal to binary using IEEE 754 double precision format, step by step. So step 1, convert to binary, base 2. You can watch previous video to learn how to convert decimal to binary using divide by 2 method. In our case, it is 1001 in binary. Step 2, normalize the binary representation of the number. So how do we normalize it? We shift the decimal mark 3 positions to the left so that only one non-zero digit remains to the left of it. Up to this moment, our 3 components, sign, exponent, and mantissa, are as following. Sign is 0 because it's a positive number. Unadjusted exponent is 3. And mantissa or fraction is not normalized yet. It is 1.001. Step 3, adjust the exponent. As you remember, bias in double precision format is 1023. So adding 3 plus 1023 makes 1026 in decimal base 10. Step 4, convert the adjusted exponent from decimal to binary. Use the same technique of repeatedly dividing by 2. This is what you get in binary. Step 5, normalize the mantissa. Remove the leading leftmost bit, since it is always 1, and adjust its length to 52 bits by adding the necessary number of zeros to the right. Finally, our 3 components, sign, exponent, and mantissa, are as following. Sign is 0 because it is a positive number. Adjusted exponent is 1026 in decimal base 10, and normalized mantissa is 52 bits, seconds of zeros and ones. So we managed to formulate 9 into this form, and our final answer is this one. Let's do one more example. Now I want to convert floating point number to binary base 2 using IEEE 754 standard. Let's convert 9.1 to binary step by step. Step 1, convert integer part to binary base 2. Using divide by 2 method, we convert 9 from decimal to binary. Step 2, convert fractional part to binary base 2. This is a bit tricky because for integers we use divide by 2 method, but for fractional parts we use multiply by 2 method, and we stop multiplying when we get a fractional part that is equal to 0. Let's give it a try. We convert 0.1 to binary base 2. 0.1 times 2 makes 0.2. We write it as 0 plus 0.2 because we use fraction parts for multiplication. We take 0.2 and multiply it by 2, that makes 0 plus 0.4. Multiply 0.4 by 2, that makes 0 plus 0.8. We take 0.8, multiply by 2, that makes 1 plus 0.6. 0.6 multiplied by 2, that makes 1 plus 0.2. We take 0.2 multiplied by 2, that makes 0 plus 0.4. It's like an endless loop because we never get a fractional part that is equal to 0, so we lose precision. It is as same as when we divide 10 by 3 in decimals, we get 3.333, etc. So to understand, I will show you quicker way. Go to Google and type decimal to binary and click on the first link. Type 0.1, click convert. It will give you binary base 2 version. If you try to copy binary version and now do the reverse sync, you will not get exact 0.1. That's why I'm saying we lose precision when converting some fractions to binary. Let's get back to our example. According to IEEE 754 standard, in Mantissa we have 52 bits. We will continue multiplication by 2 53 times and we will get this. Step 3, we combine integer and fractional parts. Step 4, normalize the binary representation of the number. We shift the decimal marks 3 positions to the left, so only one non-zero digit remains to the left of it. Up to this moment, our 3 components, sign, exponent, and mantissa or fraction, are as following. Sign is 0 because it is a positive number. Unadjusted exponent is 3. Mantissa or fraction is not normalized yet. It's a long number that's shown in the bottom of the screen. Step 5, adjust the exponent. We need to add bias to normalize, and we know that bias in double precision format is 1023. So adding 3 plus 1023 makes 1026 in decimal base 10. Step 6, convert the adjusted exponent from decimal to binary. Use the same technique of repeatedly dividing by 2. This is what you get in binary. Step 7, normalize the mantissa or fraction. So remove the leading leftmost bit, since it is always 1, and adjust its length to 52 bits by removing the excess bits from the right. If any of the excess bits is set on 1, we are losing precision. Finally, our 3 components, sign, exponent, and mantissa, are as following. Sign is 0 because it is a positive number. Adjusted exponent is 1026 in decimal base 10. And normalized mantissa is 52 bits, sequence of zeros and ones. So we managed to formulate 9.1 into this form, and our final answer is this one. That's it. Thank you very much for watching the video. If you enjoyed the video, please hit the like button and subscribe to my channel.